Good morning, gentlemen. Today, we are going to cover the last topic in our unit on energy. Don't worry, no test tomorrow, I promise. But there will be a quiz on Friday, so make sure that you pay attention and that you study. In any event, today we're going to talk about a different form of potential energy that we very oftentimes kind of ignore, and that is what we call elastic potential energy. When you have a spring or a rubber band or a bungee cord or anything else that has some form of stretchiness, not the corona, I promise, then you store energy actually within this object, okay? So here I have a little slinky, okay, and you can see it here on the screen, okay? And it is at its rest position, okay, and there it is, so on, okay. Now, if I take some kind of mass and I hook it on, all right, I'm stealing my kids' toys here, but I stretch it out. Now I know you can't really see this in the video, in the image here, all right, but obviously the spring has stretched quite a bit when I've done this. Now, what have I actually done? I've actually applied a force, the weight of whatever this thing is, to the spring, and I've caused it to stretch in this case. And so because I've applied a force and I've made it move through a distance, I have done work on the spring, okay? So whenever work is done on a spring in either compressing or stretching it, I store potential energy within it. Now, the relationship here is actually kind of a neat one, all right? If you were to graph the relationship between the force and the distance the spring stretched, not the length of the spring, mind you now, but the length that it has stretched. So for example, if the original bottom of the spring is here and I pull it down a little further, it's this distance here, all right? The distance between where the bottom was and where the bottom now is. That is the x value in this case. How far is the spring stretched? This relationship was actually discovered by a guy by the name of Joe Hook. All right, he was also a ship's captain, so you can call him Captain Hook if you want. But he wasn't really, I promise. But in any event, Hooke's law says that the relationship between the force and the displacement of a spring is F equals kx, where k is the spring constant. Now, the spring constant is not a universal constant. It's not something that you can look up on a reference table. It varies depending upon the spring. You have really tiny springs that you find in clocks and watches and things like that. You have massive springs that you find in garage door openers and that kind of thing. And they all have their own and unique and different spring constants. The spring constant is dependent upon what the spring is made of, how tightly wrapped the coils are, how thick the wire is that makes the spring up. And so a whole host of factors go into determining the spring constant for a particular spring. Okay, no two springs have exactly the same spring constant, although of course you can have two that are fairly similar. Okay, so F equals kx, the spring constant. That brings us to example number 8. All right, so let's see how we would use this in terms of a physics problem. By the way, Hooke's law is found on your handy-dandy New York State reference tables, so be sure to use that for Friday's quiz. So example 8 says, a block suspended from a spring causes the spring to stretch 0.20 meters. If the spring constant is 200 newtons per meter, what is the mass of the spring? Okay. All right, so what have we got here? Well, in this case, we go forth and again, we make ourselves a laundry list. We'll start with our value of delta x. Now remember, this value is how far the spring has stretched, not the length of the spring itself, but how far it is stretched or compressed. In this case, stretched. So delta x in our example is 0.20 meters. The spring constant of this particular spring is 200 newtons per meter. Now remember, this is not a universal constant, but just for the spring in example number 8. And we're looking for the mass. Now, you may recall, Hooke's law does not include a term for mass. It has a term for force, the spring constant, and delta x. Now we have the spring constant and delta x in our laundry list. But we also know that the force that we're applying to the spring in this example is weight. We know that weight, of course, is equal to mass times the acceleration of gravity. And so F equals kx, W equals kx, and now, of course, m times g equals kx. We can rearrange this equation algebraically to solve for the mass as k times delta x divided by the acceleration of gravity. Now, I didn't include units here because the spacing wouldn't allow me to, but the mass is going to equal 200 newtons per meter times 0.20 meters divided by 9.8 meters per second squared. All right, and if we do the arithmetic there, we end up with a mass value of 4.08 kilograms. All right, 4.08 kilograms. Now, so notice we haven't talked about potential energy yet here. The elastic potential energy is given as or by the formula PE equals 1/2 kx squared, where the k is still the spring constant that we talked about previously, and x is still the distance that the spring actually stretches or compresses. Now, the derivation of this formula is not important at this level, and so we're going to ignore that for now. But for those of you in pre-calculus who have already started talking about derivatives and integrals, all right, the formula for elastic potential energy is the integral of Hooke's law. All right, F equals k times x. The integral of that is PE equals 1/2 kx squared. All right, if you were to take the derivative of this equation, you would get F equals kx. But again, the calculus is not an important part of this. I just want you to know that there is a relationship, that these formulas weren't just pulled out of the air. The formula for elastic potential energy is indeed found on your handy-dandy New York State reference tables, so don't forget, again, to use them on your quiz on Friday. This brings us to example number 9. All right? We're going to use the same set of data that we used in example number 8, but this time we're going to ask, what is the potential energy of the object on the spring in example 8? Now, by this, I mean the elastic potential energy, not the gravitational potential energy, because we don't know how high above the ground this spring is suspended. So just the elastic potential energy here. So what is the potential energy of the object on the spring in example number 8? So again, we'll start with the whoops, come on, whatever. We'll start with example number 9. Make our laundry list. We've got delta x is 0.20 meters. No surprises there. All right, we already know that. The spring constant of this particular spring is 200 newtons per meter. And we're looking for the elastic potential energy of the spring. So PE is our big fat question mark in this case. We know the formula for elastic potential energy is PE equals 1/2 times K times x squared. And so substituting in for that with units this time, we have 1/2 times 200 times 0.20 meters squared. 0.20 squared is 0.04. 1/2 times 200 is 100. 100 times 0.04 leaves us with an elastic potential energy value of 4.0 joules. Okay, so try the math. Make sure you get this on your calculators so that you can be prepared for the quiz on Friday. Now, your homework for tonight, please, is to do questions 10 and 11 on the energy homework sheet. All right. Again, I will collect these next week on April 1st when we get back to school. Okay. All right. Tomorrow, gentlemen, we will start our unit on electricity. Be ready. I miss you all. I wish we were back in school. This is starting to get a little crazy. I want to go back to work. Yeah, too many days in the bunker. All right. Have yourselves a good one, and I will see you tomorrow.